Welcome, everybody. Good afternoon. I'm Dave Thilbrook from the Department of Fundamental and Theoretical Physics here at Australian National University, and this is the first seminar for this year of our AIP Theoretical Physics Seminar Series. I'd like to start by acknowledging the people of the Ngunnawal Nation, the traditional custodians of the lands upon which ANU is located here in Canberra. And of course, we acknowledge the traditional custodians of lands all around Australia. As many of you would be aware, I think, this series of talks is organised on behalf of the Australian Institute of Physics Theoretical Physics Group with the intention of promoting important ideas in theoretical physics, concentrating on theoretical physics or experimental physics that is of interest to Australian theoretical physicists or theoretical physicists around the world. We've now been operating for 3 years. This will be the 4th year. We started in 2021, and we've had some very good presentations from good theoretical physicists and experimentalists. And our intention was to provide a forum to keep theoretical physicists in Australia up to date, so to speak, with what their colleagues are doing around Australia and what's happening overseas, which may be of interest to them, and hopefully to maintain or stimulate a dialogue between us from various universities around Australia. So if you wish to keep up to date with what's happening in theoretical physics around Australia, you're very welcome to join the theoretical physics group of the AIP. You can do that very easily via your AIP login page if you're a member of the AIP, and if not, you might perhaps consider joining. Okay, so now with those instructions and preamble out of the way, let's perhaps do some physics. Today's speaker is Dr. Michael Hall, one of my colleagues here at the Australian National University. I've known Michael for many years. We met originally at one of the very first conferences of the Australasian Society for General Relativity and Gravitation, which is now affiliated with the AIP, shortly after its foundation, at which Michael gave a fascinating talk on the work he was doing at that time with his colleagues, which we loosely called exact uncertainty. It was a really interesting approach, and his work was widely recognized for its innovation, as it represented a new and original approach to some of the fundamental problems of quantum mechanics and gravitation. I believe it even rated a discussion in New Scientist, didn't it, Michael, in the early 2000s, 2002
yes,
or 2003, yes. I suspect, I think.
Yeah, or 2005, certainly the early 2000s, yeah. Yes, I remember that meeting.
So, yeah, so that was a feather in the cap. So in 2016, Michael and his colleague, Marcel Reginato, published their book entitled Ensembles in Configuration Space. I have my copy here, just to shamelessly promote it on behalf of Michael. Here it is.
Yeah, right. Wow.
And it's if hopefully you can access that in your university library or buy a copy. But if you can't access your university library, perhaps you might give your librarian a nudge. It should be in every Australian university library, I think. So if you are interested in some of the most fundamental aspects of how we interpret and apply physics, that book is definitely worth a read. It describes an approach to physics that is very broad in the sense that it can be applied to a wide range of systems, classical systems, which we might regard as deterministic, but also to systems of uncertainty, to discrete systems, systems of particles, field theories, and full quantum theories. So definitely worth looking at if you're interested in those fundamental subjects. Michael's also written an excellent book on relativity, which I think is one of the best I've read. And as usual for Michael, takes an interesting and an original approach to that field, and he's authored over 100 scientific papers. Today, as you would have seen in his abstract, he's going to be talking about correlations in quantum systems, initially by means of a simple argument based on joint probability, which is capable of recovering the standard Bell inequality predictions. As probably all of us know, Bell's inequality establishes limits on the correlations between measurements that can be made on entangled quantum systems if the principles of locality or realism were to be regarded as holding true for all physical systems. I think that's probably the best one-line definition I can think up for Bell's inequalities. Michael will undoubtedly do a better job. Bell first proposed this inequality in the 1960s, 1964, I think. But it's now evolved into a number of different forms, inspired largely by the requirements of experiment. And the philosophical interpretations, I think it's true to say, of these experiments on Bell inequalities in general are subtle and sometimes philosophically challenging. So Michael's approach to the subject, I'm sure, will be refreshing and very useful. So to tell us more about this fascinating area of physics, Michael's talk today is entitled Why Quantum Correlations Are Shocking. Thanks, Michael. Over to you.
Thanks, David. The introduction. Yeah, the shocking in the title comes from when something that Niels Bohr, grandfather of quantum mechanics, said to Werner Heisenberg, those who are not shocked when they first come across quantum theory cannot possibly have understood it. And Feynman said sometime later that nobody understands quantum mechanics. So it's been that way for a long time. But recently it's been getting more press with the award of a Nobel Prize. So this is work I've just had accepted this morning, actually, in the American Journal of Physics. So that'll be appearing a little later this year. Right. Let's get started. So the outline, I'll give a little bit of history, several slides, talk about Einstein, Podolsky and Rosen. I'll be talking about John Bell and a few others. Then I'll be presenting the main part of the talk, which is there's a lot of ways of trying to derive Bell inequalities, which does lead to a lot of philosophical discussion and various distinctions, subtle distinctions. I'll try and avoid those in a way by showing how you can obtain this very important inequality that's used in quantum cryptography, for example, and quantum random number generation, just from two minimal assumptions that are very appealing physically. And that inequality, it's violated by some quantum correlations. Now, I wanted to say, though, work derives from an old paper by Arthur Fine in 1982 and had some, well, simplifications perhaps, and but that's where it gets its impetus from. And Fine quite likes this paper. I found out again this morning that he was a referee on it. He gave some very good comments. He's 86 now. It's amazing he's still working. He's a philosopher in Illinois. So we've got these assumptions. This Bell inequality is violated by that. And so there's something wrong with these assumptions as far as they apply to our world. And that brings up the issues, are there faster than light effects? We have to choose between that or perhaps our measurement choices that we think are freely made when we do experiments and not independent of perhaps far distant systems in our universe. Or we have to accept that some system properties cannot be measured jointly. And what's interesting, this is so even if you can define a joint distribution for them, even in quantum mechanics. Okay, so that's what I mean by the shocking, that these implications, if you think classically, which I guess many of us don't any longer, but if you do, they're somewhat shocking. All right, so let's go back to 1935. There was a famous paper by Einstein and two collaborators, and they proposed following thought experiment. We have two particles, a purple particle and a green particle, and we correlate them when they're close together, perhaps via some interaction, and then separate them. And the correlation is such that their total momenta and their relative positions are sharply defined, very accurately defined in this thought experiment. And quantum mechanics is on board with that. Yeah, you can do that. Then if the momentum or position of the first particle, the purple particle, is measured, measure one or the other, you can then infer, because of these correlations, if you measure the momentum, you get a value. you know the sum, therefore you can infer a corresponding momentum for the other particle. If instead you measure position, then you've got that value, you know the difference in the values that's sharply defined, you can infer fairly sharply a second value. So that's the experiment. And then what do we think about it? Well, EPR said, can it really be the case that the real state of affairs, what is the case about the second particle, can that depend on whether we measure the momentum or position of the first, or did those values already exist? They were real in some sense for this second particle, which may be very far away from where we make this measurement. And EPR, their answer was, it can't depend on it. That's ridiculous. They therefore concluded that the position and momentum of this particle have sharp values. Quantum mechanics doesn't allow you to have a state with simultaneously sharp values of conjugate observables. So quantum mechanics is missing something. It's incomplete. And that paper created quite a few reactions at the time and ongoing ever since. It's a very well-cited paper. And I'll start off with those by Niels Bohr. Here he is again, kicking back with Einstein at one of the Solvay congresses. They had many arguments about the meaning of quantum mechanics. So as we know, Einstein's conclusion was quantum mechanics is incomplete. If we want to avoid this spooky action at a distance as much as possible, the momentum and position of that other particle must have predetermined or at least well-defined values independently of the measurement made on the first particle. But Bohr took quite a different view in a couple of papers, and his argument, quantum mechanics is complete, and that the flaw in the EPR argument from Einstein is you can only ever measure P1 or Q1. You can't measure both because of complementarity. The experimental apparatus you need to even to sharply define momentum is incompatible, physically incompatible with the apparatus you need to get a sharply defined position measurement. So you have to choose to measure one or the other. Therefore, you can only infer one or the other, not both. You can never infer both. So there's no need to ascribe joint properties. Quantum mechanics is complete. Wendell Furry, of Furry's theorem, had a different sort of response. He said quantum mechanics is wrong, must be wrong. What happens is the correlations, they're going to break down as soon as you move those particles apart. There's going to be some randomization of phases or something like that. So there is no problem. Well, Furry turned out to be incorrect himself, but he did raise a very good point. You've got to do the experiment and see what happens. And then Schrödinger had a take on it. He wrote a couple of papers in response that really got him going. And he didn't like the result, but he thought it had to be accepted. So he used words like discomforting. He introduced the word entanglement, now used throughout discussions in quantum information. The idea that the two systems as a whole with their correlations is somehow more than, you can't ascribe it just to properties of the parts in isolation. He introduced the idea of steering, which was taken up later by Howard Wiseman to develop important quantum information protocols. And he used the words that this EPR effect, it's repugnant to some, but it's unavoidable. And I haven't put a picture of Schrödinger because we hear a lot about Schrödinger's cat. And I thought a lot of people don't know Schrödinger didn't have a cat. That's probably why he said such mean things about them. He had a dog called Barney, and that's Barney there. So Schrödinger's conclusion, he said on another occasion, I regret I ever have anything to do with quantum theory. So he certainly thought it was, you could say he thought it was a shocking theory. Okay, we jump forward almost 30 years to John Bell. John Bell went one further than, he sharpened the paradox raised by EPR about whether quantum mechanics is complete or not. There's certainly something funny about it. So he used some work by David Bohm to replace, instead of considering sharp position and momentum correlations, he said, let's look at sharp and admittedly actually said, let's look at spin half particle correlations. But I'm going to take advantage of the fact that that's formally equivalent to polarization correlations. So I'm misrepresenting Bell slightly, but we have him in spirit here. So here's John Bell. He says, well, let's take two photons, two photon state. We have a purple one and a green one separated by a large distance. And they can be correlated according to quantum mechanics such that if I make a measurement of linear polarization at some angle theta to the vertical, say, I will know, I can predict, I can infer what the polarization of the green photon will be at that same angle. And it doesn't matter what angle you choose, there's this perfect correlation. So that was his modification of the experimental setup, which is important for violating Bell inequalities, as it turns out. And he made some assumptions, which I won't talk about in detail, but just to give you a flavor, there's that assumption that you've got the perfect correlations if you measure at the same angle. If you measure something at one angle, you know what's happening at that angle for the other particle. You assume that there's predetermined values of these polarizations given by, call it a hidden variable, something that isn't in quantum mechanics, say. And you assume that the predetermined value, whether your photon here passes through a polarizer or not at some angle, that's independent of what angle you might actually choose to measure this one. That's a locality type assumption. And you also have another assumption that whatever it is that's determining whether a photon will pass through or not a polarizer at a given angle, that's independent too, whatever of what you measure on either of the photons. In other words, the hidden variable, you have free will, if you like, there's consistency with free will, you can measure whatever you want, and that's totally independent of what's going on at the level of the systems and the hidden variable. You make those assumptions, and then you can make a prediction about how the correlations, the statistical correlations between if I measure at some angle theta here, some angle phi here, you can say they must satisfy certain inequality, statistical inequality. That inequality contradicts quantum predictions. So, and so now he's somewhat sharpened, you can see already the EPR paradox, because you're now saying if you do want hidden variables, which Einstein would like, you would like some sort of locality property of such a model. You would like some sort of free will or free choice property. You can't have them all if there's perfect correlations. Okay, so you'd think that might slow down the debate, but it didn't quite. So just a little bit more of history. You can't test that original Bell inequality that he derived because you can't guarantee experimentally. You need that assumption that those perfect correlations are there. Of course, in the lab, you can get close, but you can't get there. So you need a different inequality. So in 1969, John Clauser and co-workers, Horn, Shimony, and Holt, came up with such an inequality, and Bell essentially came up with the same one within a year. And of course, that's what I'll be mainly talking about, what you need to obtain this inequality and what it means. The experiments were done in 1972 by John Clauser and a colleague. In 1982, a much more compelling experiment in some of the technical details by Alan Aspey. There were some loopholes in these experiments. You were detecting photons after all, and they're hard to detect accurately, especially back in the 70s, 80s, 90s, 10s. So, or zeros at any rate, the noughties. So there were some loopholes. For example, you can't detect all the photons, you're missing some. So are the probabilities, the correlations that you measure actually representative of what's going on in the background, because you're missing some. Perhaps there's a bias. So 2015, these loopholes were closed essentially as far as possible by 3 experiments, all came out in that year. There was one led in particular, I mentioned Anton Zeilinger's name, who's also responsible for a lot of breakthrough experiments on quantum correlations and entanglement. Further, and I'm not giving references here, these violations, well, they're certainly of interest if you're want to try and understand quantum mechanics, but they turn out to be of practical interest as well. Somewhat practical interest. There are some commercial resources available now you can buy off the shelf. If you violate this inequality or other Bell inequalities, you can get a guaranteed generation of a secure cryptographic key in quantum mechanics. The degree of bigger the violation, the more secure key. And that's guaranteed secure essentially by the laws of nature now, which is very cool. And similarly, there's a way of generating truly random numbers rather than pseudo-random numbers, again, guaranteed by violation of a Bell inequality and the degree to which it's violated and the laws of physics. So then just in 2022, the Nobel Prize was awarded to John Clauser, Alan Aspey, and Anton Zeilinger. Basically experiments with entangled photons that established the violation of Bell inequalities and pioneered quantum information science. Of course, Bell would have knocked one of those off their perch and claimed it, but A, he would have been 90 at the time, and B, died in 1990. So he missed out, but I'm sure he approved in spirit. So it's now been recognised at a pretty high level, the value of these inequalities. Okay, so these inequalities get violated. Why is that shocking? It's let's go through it. First, when you look at various derivations of the inequalities, they make assumptions that many different sets of assumptions are possible. A lot of them, perhaps if you're teaching students in particular, you sort of simplify and make assumptions, stronger assumptions than you need. Also, people make assumptions, there's determinism, parameter dependence, that are not only strong, but sometimes they're the same assumptions with different names. This joint probability distribution, I'll be coming back to. That's where I'll be starting off from. It's due to Arthur Fine. Hidden variables, of course, we've mentioned, various other names. So when you're trying to work out what it all means, completeness, there's a lot of possibilities, and that makes the discussion more difficult in a way, although they're very interesting discussions. So there's some of them. So what I want to present here is the idea we can replace all these possibilities in different sets by a particular set of two, what I call minimal assumptions. They're minimal, they're natural, seem natural. And in fact, one of them, in fact, holds related to no signaling, and one is violated. And that the degree to which that assumption is violated is directly proportional to the degree to which you violate the CH-SH inequality. I should have said this is Clauser, Horn, Shumany, and Holt, the first paper with this inequality in it. We call it, and it's also an example of what is called a Bell inequality now. There are many, but this is the workhorse one used in most applications at present. All right, so they considered a fairly general experimental scenario, CH-SH scenario. And how does it work? We have two observers, Alice and Bob. They each receive a system on each run of their experiment. Alice makes one of two measurements, A or A prime, gets a result. Bob does the same. He measures B or B prime, just two different physical quantities on each run, and he gets a result. And the simplest, two simple examples are on each run, they get a dice. Alice gets a purple die, I should say, and Bob gets a green die. And they roll the die. They each roll their die, and they can do it with their eyes open or their eyes shut. That might seem almost silly as an example, but it's useful for two reasons. One is just that I want to make the point, it doesn't matter how many results your measurements have. In this case with the die, you get a result from 1 to 6 if they're 6-sided die. The derivation I'll give here doesn't require you to restrict the number of values of outcomes. And the other thing is pedagogically, when you want to give weird models for what would be going on behind the scenes, dice are very simple things to think about. And I use that in the paper. I won't use it here. I'll concentrate for a physics audience on physical polarizations of photons. And so in this version of the CHS experiment, You have a purple photon and a green photon. One goes through a linear polarizer oriented at some angle to the vertical. Alice can choose two different orientations between those when she makes a measurement, and it either goes through or it doesn't. That's the result. Yes, it goes through, or no, it doesn't. Similarly for Bob, he chooses two angles. It either goes through or not at each of those angles. They can then run their experiment on many runs, making different choices each time, A or A prime for Alice, B or B prime for Bob. From that, they get a heap of relative frequencies, and they can estimate probabilities, which, if you've got a theory of the correlations, these probabilities should be predicted by the theory, and you can compare them. So they're measurable, and there's 4 of them. Alice measures A, Bob measures B. They'll give you that over many times, estimate that, all the way to Alice measures A prime, Bob measures B prime. So that's the scenario. Now we come to these assumptions, which I'll introduce slowly. There's only 2 of them. First one is very simple and sort of pretty obvious and, in a sense, indisputable. And it's just saying that those measured correlations, not some hidden variable type correlations, those measured correlations can't be used to signal from Bob to Alice. So Alice's statistics, she can measure A or she can measure A prime. No matter which one she chooses to measure, and no matter what Bob's doing at his end, on his system, his photon, for example, her statistics will remain the same. So Bob can't say, well, if I measure B, she'll see different statistics, to if I measure B prime, I can now communicate with her. We're going to rule that out by assumption. What does that mean mathematically? Well, here's this distribution for if Alice measures A and Bob measures B. They'll have this joint distribution. So Bob's measuring B in this case. If you sum over this distribution, sum over B's results, you'll find what Alice's local measurement distribution is for A. But what if Bob measured B prime? Well, this is now your relevant measured probability distribution. We sum over Bob's results for B prime. We should get back the same distribution. We have to get back the same distribution if no signaling holds. That's what it means if Alice measures A, the statistics don't depend on what Bob's doing. Similarly, if Alice measures A prime, you have these relevant measured distributions, and the distribution Alice sees doesn't matter what Bob's doing, measuring B or B prime. And the good thing about this first assumption, well, first it's predicted by quantum mechanics, thank goodness, because otherwise it wouldn't be consistent with special relativity or general relativity as we know it, assuming that Alice and Bob are in space-like separated regions when they do their experiment. And also, even better, it's been experimentally verified. So to within statistical errors. So in that sense, we know it's actually true. We're not, it'd be a hard job to say, hey, there's something wrong with no signaling. You'd have to overturn experiments. And it is interesting, actually, when it came to the loophole-free experiments I mentioned, the 3 done in 2015, the first of those had very little statistics. And somebody went through their results, a couple of people, and said, hey, if we look at that, no signaling's not very well satisfied. There's a lot of statistical error here. Is that really an error or does it hold? So they did more analysis and said, yeah, it holds with good probability. More importantly, that the next 2 loophole-free experiments that came out that year, they had more photons to get good statistics, but they verified it and they wrote that they'd verified it, and it's now become realized that when you're testing Bell inequalities, you do need to test no signaling. All right, you'd expect there to be another no signaling assumption from Alice to Bob. Actually, our second assumption will imply that as well. So Bob's statistics aren't going to be affected by Alice's choice of measurement, but we'll come to that. First, I want to talk about some important consequences of this no signaling assumption. And they're pretty simple consequences. I'm not going to prove these things. I'm just going to state them. The proofs are just a couple of lines. That assumption, no signaling from Bob to Alice, which we know holds empirically, theoretically, philosophically, we sure want it to hold, unless we're Hugh Price, possibly. It holds if and only if there are two joint probability distributions, one for when Alice measures A and one for when Alice measures A prime, and then for Bob's outcomes. If there are such distributions exist, such that they give back the measured probabilities as marginals. What do I mean by that? Well, let's have a look at this. Alice has measured A, Bob measures, well, Bob can measure B or B prime. We assume there's a joint distribution that if we sum over the outcomes of B prime, we get back this measured distribution. Similarly here, if we sum this distribution over B, we'll get back the relevant observable distribution for A and B prime. So, and this one satisfies these properties. We take the marginal, we sum over B prime, we get back this measured distribution, and similarly here. And this is an if and only if relation. So if you've verified no signaling holds experimentally, you've verified such distributions exist. And actually, typically, there can be many of them. And what I'm going to say, it doesn't depend on what you take to be those distributions, as long as we just know they exist, and any and all such distributions will do for our purposes. But I will give you one example, which is nice because it's simple and universal. If no signaling from Bob to Alice holds, then there's a well-defined, Alice's statistics are well-defined no matter what Bob does. These distributions just measured, I multiply them together, divide by that, call that P0. That satisfies this property. Similarly here, I multiply these measured distributions together, divide by this probability, which is well-defined no matter what Bob measures by the no signaling assumption. These will do. And what's interesting is even quantum mechanics. You know, these probabilities are measurable, all measurable. They're all predicted. You can bung them in and get that out. Similarly here. But it's only one example, and there are other examples. Of course, this will apply to all examples. Right. So we have no signaling. So we have two distributions like this. So what can we do with them? We can just apply some simple classical probability theory. We can derive this inequality for the probability of B equaling B prime. I can calculate that from here. So Alice is measuring A. I have this distribution which exists by no signaling. I can work out that probability. Whether or not I can measure these, I can work out this probability. And then this holds. It's not a surprising result. I'll talk a little bit more about it later. It's very easy to show. I'm not going to bother with it in a talk, because maths derivations in a talk are a pain. Okay, this distribution exists by no signaling, or many such exist. For any of them, you can show that this inequality also holds. And again, I'll talk about it a little more later. So this is the result that I need, the key result, all coming from that one assumption that we know is true. This is true. Okay. Whether B equals B prime and Alice is measuring A, or whether B is not equal to B prime when Alice is measuring A prime. Now we come to our second assumption, which joint invariance. And I'll explain that. First, just recall the no signaling assumption has this form. Alice's statistics aren't affected by Bob's choice of measurement, and we know that's equivalent to these existing. Our second assumption has a very similar form. Bob's joint statistics for B and B prime, which we know exist again because these exist, are not affected by Alice's choice of measurement. Okay, so we can, from this, we can calculate this distribution just by summing over A, summing over Alice's results, possible results. Here we can calculate this distribution by summing over Alice's possible results for A prime. This joint invariance assumption just says you get the same answer either way. It doesn't matter what Alice measures, these joint statistics are the same. So you can see they have a similar flavour. This one sort of seems obvious because of relativity. This one seems sort of obvious, but it's the one that's going to be a problem. We know this holds, remember, empirically. Turns out this doesn't hold if you violate a Bell inequality. And of course, because these distributions are the same, when I calculate the probability of B being equal to B prime, in either case, Alice measures A or Alice measures A prime, I should have said earlier, that's what this prime is indicating as a mnemonic to simplify notation. No prime, Alice is measuring A. A prime, Alice is measuring A prime. Okay, so these must be equal. That's the content of the second assumption that we need. This is the equivalent content. That's a special case. Right, now we're ready. We've got our two assumptions. Yeah, does that one hold? Well, okay, now from the first assumption, you'll remember we had two simple statistical inequalities that hold. So this just comes from the no signaling assumption. They both hold. But from the second assumption, this distribution here, the second assumption essentially says, hey, that's equal to this. The probability of B not equal to B prime if Alice measures A prime is exactly the same as the probability that B is not equal to B prime if Alice measures A. So the only difference here is we've removed that prime using the second assumption. Okay. And here we've already got the beginnings of a conundrum, and it's this. Suppose that A equals B, suppose the measured probabilities we find are such that A equals B, the probability is very high. And also the probability that A equals B prime, that probability is very high. So, they're both close to 1 in some sense. Add them up, so close to 2, subtract 1, close to 1. Wow, the probability that B equals B prime is very high. And you can see how obvious that is. If A is very likely to be equal to B and to B prime, then certainly B is going to be very likely to be equal to B prime. These are really simple inequalities, but that's what it's telling you. But now you've got the same sort of thing here. Suppose these measured probabilities are also close to 1, then A is very likely to be, this A prime is likely to be the same as B, but A prime is not very likely to be equal to B prime. So it's very likely that B doesn't equal B prime in that case. And that's what this inequality tells you. And you say, fine, okay, these all have high probabilities. What then? Well, then I'll get this is certainly going to be greater than 50%. It's going to be very likely. This is going to be greater than 50%. So it's very likely that they're equal. It's very likely they're unequal. Seems that we have a problem. And the only reason we can't say there's a definite problem, or that we may resist, is that, hey, this is talking about things we haven't actually said how we're going to measure them. PB equals B. This might be two observables. We don't know how to measure jointly. But we can fix that. We just add these two equations. And if we do that, this plus this equals 1. You pull all the ones over to one side. You've got a sum of your measurable probabilities. You can get this from your measurements in the CHSH scenario. The sum of these probabilities is less than or equal to 3. Now we only have measurable probabilities appearing. We can test this. And this is a particular form of the CHSH Bell inequality from those two assumptions, which I'll come back to. First, of course, it's worth going over, especially for those familiar with Bell inequalities, and say, that's a form of the inequality? I haven't seen that. So here's the form I gave, following from our two assumptions. The more standard form is you take the probability of A equals B, subtract the probability that A is not equal to B. Again, these are experimentally determined, and you subtract them. This ranges between -1 and +1. It's just a measure of correlation. That equals +1 if A equals B with probability 1, perfect correlation. That equals -1 if there's perfect anti-correlation. Okay, so we can, these are related to these very simply. And so we can turn this inequality into 1 for these correlation measures, which sum the first 3, subtract the last. It's always less than or equal to 2, and that's the more standard form of the CHSH inequality. And we call that sum and difference S. So that's what we need to measure in, or that's what is measured in experiments generally. It's the same as the measuring of these probabilities. Okay, so quantum mechanics says you can get values of S much larger than 2, up to 2 root 2. Theoretically, it's very interesting that you could get values. This could be equal theoretically, possibly, to 1, to 1, to 1, to minus 1, and you'll get the value of 4 here. Quantum mechanics doesn't let you go that far, but and it's very interesting that it doesn't, but that's another story. How do you do that to achieve this maximum value? Well, if you're doing it with entangled polarizations and you choose your entangled state correctly, you can just set your polarizations at particular angles, do the experiment. And because there's errors in what you can actually achieve experimentally, you can get close to this with additional assumptions. Not as close to 2 root 2, but definitely greater than 2, even if you do loophole-free experiments. So that's what we find. So that tells us the inequality is violated. We got it from 2 assumptions. One of those assumptions has to fail. Maybe both of them? Well, no, because we know the no singling assumption holds. Easy to test that too from the measured correlations. So that tells us that it's the joint invariance assumption that fails. This probability that exists as a consequence of the no singling correlation isn't equal to this probability. So that's what we have to interpret. What does it mean? Okay, before I go into what does it mean, just one slide on just a couple of interesting points, perhaps. Remember, just from the no singling assumption alone, we got these. This is going back to those 2 original simple inequalities. I have not made the second assumption that this P prime can be replaced by a P. So I don't make the second assumption. I just add these without making that assumption. Use the fact that if B is not equal to B prime, that's the opposite of, I've made a mistake. This should be B equals B prime. My apologies. But anyway, you add them, do the right thing, and you find that the difference between the probability of them being equal when Alice measures A, if you subtract the probability of them being equal when Alice measures A prime, so she's doing one or the other, you can subtract these. It's got to be greater than or equal to the amount of violation of the inequality. Remember, the inequality based on the 2 assumptions says this has to be less than 2 or equal to 2. If it's greater than 2, there's a violation, and that amount of violation sets the minimum displacement, the minimum, if you like, non-local effect. I don't like non-local, so I won't say that. All right, so there's a direct link. So that's another nice thing, I guess I wanted to point out about this means of derivation. One assumption fails. How much does it fail by? It's directly set by the degree to which you violate the inequality. And I'll just go quickly through this. Don't worry if it doesn't make too much sense. It's just for people who are familiar with local realistic theories. If you make assumptions that there's a hidden variable lambda that determines all your outcomes, so all your photon polarizations, or the results of all your dice rolls, whatever. And lambda determines the outcome of A prime, B, and B prime by suitable functions. And you make assumptions related to locality and free choice. You can show that you can choose your probabilities P and P prime such that these are equal. Okay. In an obvious way, because this says the outcome of measuring B is little b. If you have a certain value lambda for your hidden variable, it just says it determines the result. The result's going to be some result B. And I'm missing a sum, aren't I? Yeah, all right. Don't worry about the formula too much. The point is that these 2 things turn out to be equal in any such model. If they're equal, their difference is 0. If the difference is 0, S has to be less than or equal to 2. So there's no violation. In other words, with such a model where these are determined by a hidden variable, there's no model. So that's just recovering a known result. Okay, and with a typo, for which I apologize. All righty, so we're nearly at the end of the talk. I don't know how fast I'm going. I intended it to be well under an hour. I hope it's not well under half an hour, that I haven't talked too fast. What are the possible explanations? for this failure of the second assumption. And I want to point out again, it's only one assumption that we're looking at now. We don't have to worry about some shades of subtle distinction in definitions and meanings of various sets of things. There's no hidden variables in here. There's no determinism. There's no, there's no anything really except no singling and joint invariance. And we know from if this inequality is violated, this holds. The probability that B equals B prime is different for when Alice measures A and when Alice measures A prime. We have a correlation. Okay, so we just have to look at that one thing. And of course, though, the explanations you can give for it relate back to some of these subtle distinctions, but really there's only three possibilities I'll argue for. And maybe people want to talk about other possibilities, we'll see. One is obvious. If Alice's choice of measurement sends some signal to Bob's lab, and if their labs are far enough apart on each run, then it's going to have to be a faster than light signal to get there in time. So if this is the explanation for what's going on, we get the grandfather paradox and other relativistic paradoxes. It's a shocking, that's a possible but shocking implication. Another possibility, well, this first possibility is about a direct cause. Something in Alice's lab happens, sends a signal of some sort, which causes a change in Bob's lab, to Bob's system, at least. But that's direct causality, but there's also the idea of a common cause. So perhaps Alice's measurement choice and Bob's outcomes have some common cause influencing them. So what she might think is her free choice of what she's choosing to measure, she can't make that. It's not independent of properties of Bob's system, in particular these probabilities. They're correlated with that choice. So that's certainly the whole is more than the parts type of thing. And John Bell referred to such a possibility as even more mind-boggling than this one. So definitely shocking, at least to classical intuition. I should say some people like this possibility. They work with it. Some people like this one. And there's another choice, and it's more subtle, which is that, sure, these exist. They exist by no signaling. We have to accept that. But they only formally exist. And maybe many of them exist, but they're all formal. They're not physical. And if they're only formal, it doesn't matter that these aren't equal. No physical ramification at all. So that's a bit odd. It's saying, yeah, all right, you've pushed me to it. Even Bohr would have to say, yeah, they exist. Okay, but they don't mean anything. Why don't they mean anything? Well, to maintain that consistently, you would need to argue that these aren't measurable as relative frequencies. They're not really physical probabilities. There's no physical joint accurate measurement of Bob's two observables, so you can repeat many times and get these probabilities. So that's the third possibility. What can we say about that? Well, Einstein would probably just want to give up there. He might throw up both hands, but I didn't have a picture of him throwing up both hands, but he's looking a little sad. But Bohr, on the other hand, he's pretty pleased because Bohr agrees there should be nothing faster than light, that you should have free choice. He writes explicitly he wants those to hold. But of course, he maintains it's his principle of complementarity for understanding quantum mechanics. You can't measure these things. These are only formal, so no problem. So Bohr's happy with the outcome of what it all means. But of course, complementarity, is another shocking, it's probably the last time I've used that word, but it was introduced by Bohr. They're all shocking possibilities, but one of them has to hold, essentially. Right, so that comes to the last slide. So just to recall, we can obtain that Bell inequality, which is our workhorse in quantum cryptography applications at the moment, and some random number generator applications, for example, from just two assumptions. no signaling and joint invariance. Violation means since no signaling does hold, experimentally joint invariance has to fail. And because it fails independently of whether quantum mechanics is true or not, of course, to derive this inequality, you don't assume anything about quantum mechanics. So even if we replace quantum mechanics as it is now by some future model that might incorporate gravity, it's still going to fail. And so if we have any good model that can explain, that predicts violation, joint invariance will fail in that model. It's with us for good. So we have to accept one of these possibilities, all of which are surprising, extraordinary to classical intuitions. And you can generalize this to an arbitrary number of measurements on each side, and they don't even have to have the same number of measurement results. You can generalize, instead of deriving inequalities between spatially separated measurements, you can derive them between temporally time-separated measurements called Leggett-Garg inequalities and temporal Bell inequalities, where these assumptions become related to no disturbance assumptions. And there's a property called non-contextuality, which I won't explain, which holds for a single system and what you can measure jointly with a given observable. And again, you make what are called non-contextual no disturbance assumptions. And again, you can apply the same approach in deriving those. Right, so thank you for listening. I'll hand back to David.
Thanks, Michael. That was a fascinating talk. Just glancing down, no questions in the Q&A just yet, so I might kick things off, or attempt to kick things off. On one of your slides, we often hear this said, and it may well be true. We hear statements like, and I think on one of your slides you kind of alluded to it, with a statement along the lines of that effectively, well, sometimes we hear the Bell's inequalities imply there is no locally deterministic hidden variables model. And I think your slide was a bit more careful. You said for values of S greater than 2. Yeah, there. So can you just make a comment? So where does this leave the status of alternative attempts at building locally hidden variable theories, such as, for example, de Broglie-Bohm theory?
Yes. So de Broglie-Bohm theory, there are different ways of formulating de Broglie-Bohm, partly in dependence on how much you're committed to it. So the normal answer is that de Broglie-Bohm theory does involve explicitly non-local effects, which you can set up. You can also make simpler toy models which are non-local and then actually calculate the difference between these in any given model. If you're fully committed to de Broglie-Bohm, though, which is I should say for those unfamiliar with it, it's a model for quantum mechanics in which everything is predetermined, but you can only make position measurements. And so you have to interact with apparatuses in different ways, depending on whether you want to get out, say, position information, momentum information, spin information, the polarization information. And when you do those interactions, it can affect properties of distant systems. So one way is to think that there's signaling going on, but if you apply de Broglie-Bohm consistently to the whole universe, then even your choice of what measurement you're going to make on a system is predetermined. And so if you like, there's a hidden variable, which is the initial configuration of everything in the universe. There's a common cause. So de Broglie-Bohm theory, you take this answer or this answer. Normally, you would just say that's what it is.
Yeah.
Some people would, well, in de Broglie-Bohm, it is a hidden variable model for quantum mechanics, this configuration of things that you don't know. There's an initial distribution of them, although there's a real one operating in our universe. You simply never know what it is, so you get statistics. So if you believe that configuration is real, you don't adopt complementarity. In one sense, you say that these distributions are, in fact, physical. They're not formal. It is something you have to worry about, and explained by one of these possibilities.
And particles follow real trajectories in configuration space, and
yes,
but there is great sensitivity to the input, the initial conditions.
yes, that's right. That's right. And there are and the deterministic values that are predetermined. If you like, if you actually had, say, I'm going to admit free will into my Bohmian mechanics, you move something over here, it changes something over there. You can't get away with that if you have an entangled wave function connecting them. So,
what about variations of, this might be out beyond the scope of the talk, but what about variations of de Broglie-Bohm theory which incorporate input noise, if you like, from the quantum vacuum? That's a generalization of the old original de Broglie-Bohm theory.
you're not talking about stochastic electrodynamics. You're talking about applying it to quantum field.
You're talking about Marshall's work. Yeah, no, not quite. But yes, there are elements of that.
Yeah, you have essentially, well, it's difficult to actually get a relativistic version of de Broglie-Bohm theory.
Yeah, I don't believe you can. I think
it's been done where you take a say a preferred time slice and say that's physical. There's a preferred frame that we don't actually have access to, or there's a thing called the flash ontology. Essentially, you have the same difficulties.
Yeah.
Your configuration space now includes a hidden configuration for the quantum field, say, which might be, say, the quantum vacuum. And the quantum vacuum is now seen as it's actually an ensemble of possible fields that's interacting with your systems. And again, the most natural way to think about de Broglie-Bohm is just that it's non-local. There's these faster than light effects going on. And in the case where you set a preferred inertial frame, those effects are faster than light in that preferred.
Well, that's interesting.
They're instantaneous in that frame.
Right.
You can also have other models for quantum correlations, not just the non-local, faster than light ones. You can set up at least toy models where your free choice is no longer free. And it's easy to do, say, for correlated states of two photons to explain your polarization models.
Right.
And in the paper that's coming out in American Journal of Physics, I give a very simple example in terms of the dice, where Alice and Bob, it turns out that Alice and Bob, they have their two dice, a purple dice and a green die, and they're rolling with their eyes open or shut, but they just happen to hate the color purple. So whenever they receive a purple dice, they close their eyes when they roll.
Yeah.
And it turns out that the dice are set up and weighted and sent to the observers in such a way that, to exploit that property and violate the CH-SH inequality, not just to give a value of 2√2 for that quantity S, but a value of 4, the maximum that's possible. So you can set up other toy models like that, and again calculate for those models how much does this inequality fail by, and and the difference between these quantities has to at least be half the degree of the violation of the inequality. So that's something that you can do for fun. I don't know for how much profit, but certainly for fun.
Your second solution, or probably the first solution, your second point on the final slide was that perhaps Alice's measurement choices and Bob's outcomes have a common cause. Is that's close to sort of superdeterminism type of philosophy, isn't it?
It is. So superdeterminism, well, Bell defined it as everything's predetermined, your measurement choices and the outcomes of measurements, all by some common cause. And it's one of those ideas that come up in the literature again and again under different names. Now they've broadened it. It's often called measurement independence, or measurement dependence. There's a dependence or correlation between the measurement and the system quantities, or hidden variables if they happen to be hidden variables. So what was the question? So superdeterminism is an example. I think of it as a special case of this second thing. There are other ways that you can get such a correlation is retrocausality, which
Yes,
some
yes.
people distinguish from superdeterminism. So the point is that there is a correlation that you want to explain between her choice and this. There definitely has to be a correlation if you violate it. If you assume these quantities are physical, that can come from a direct cause, or it can come from a common cause. The common cause could be in the future, that's retrocausality, or in the past, and that corresponds more to what most people think of as superdeterminism.
And if it comes from the past, it's physical. Is it restricted? That common cause has to propagate to the two measurement outcomes.
Well, that's up to you, but yeah, normally you're trying to avoid something faster than light happening.
Yeah,
So
yeah.
you like to make it causal.
So then, if you're trying to achieve something faster than light happening, then you've got your relativity of simultaneity argument is going to enter into that, is it not?
Oh yes, so that corresponds to if there's something happening faster than light, you've then got to get around possible paradoxes, such as going back in time and doing in your grandfather before you were born. So and philosophers like Hugh Price and Ken Wharton sort of explore those to see whether are those paradoxes really an issue, and they do a fairly good job in sidestepping possible things such as the grandfather paradox, but that's a fairly minority view. But I guess my position is you have to take all the views fairly seriously. I could also mention if you're trying to do quantum key cryptography, it basically relies on this assumption. It says that there's no faster than light effects. That's ridiculous. And of course, you've got free choice. Therefore, there's an eavesdropper can't make some sort of joint measurement on one or both of the systems to find out what really is the real state of affairs. But if you're buying a quantum cryptography apparatus off the shelf, to use it in any practical sense, you don't go around, deliberating, oh, I'm going to measure B this time, or maybe B prime, and pushing a button. That might be using free will, but in practice, you get random number generators to do it for you.
Yeah.
And it's possible that they're compromised. And so one little subfield in this discipline says, hey, all right, how much do things have to be compromised? How subtle can the effects be such that the manufacturer can give you what look like random number generators to plug in and use, and they're actually not quite random at all. That there is this correlation between the measurement outcomes and the selection of measurement. And so that's actually a practical thing to think about. So yeah, I like to try and keep my mind open, but of course I tend to go more for the third option, which I think probably most physicists do, as being it's sort of the nicest in my view, but not in everyone's view. That's for sure. Some people love de Broglie-Bohm, for example, the model you mentioned.
Yeah, no, I don't know what to make about what you said about there is no relativistic version of de Broglie-Bohm is true. I know that there were some attempts to show that relativity would be a consequence of non-relativistic equations at the basis of some form of non-relativistic equation at the basis of de Broglie-Bohm, but I don't think that work has really been very fruitful so far. I wanted to ask you a question too. In all of this,
yeah, and there's some others in the audience too, I see as well.
Beg your pardon?
There's also some now.
Oh yes, yeah. I haven't forgotten. We'll get to those. We should probably get them first. This is a very quick question. In all of these CHSH type experiments, there's also the possibility, of course, that neither detector will detect a pair of photons.
Yes.
Right. So really, your experiment is being conducted on the subset of physical outcomes where particles were jointly detected. And I often wonder, what are the hidden implications of that assumption?
Yes. Yes, you're right. Detectors always will miss at least some photons.
Yeah.
You'll notice that the inequalities I have talk about whether A equals B or A not equal to B. So if there are null outcomes, that's just a third outcome, no detection. You could handle it that way. In practice, you can take into account the inefficiencies of the detectors and say, I have to not only get a violation greater than 2, but a little bit more, depending on the inefficiency of the detector, than 2. And if it's very accurate, you only need to get a very little bit more than 2 to still come to the same conclusions that despite your your photo detectors not being perfect, I can still show that one of these conclusions has to hold. So that's fairly well known now. And the big point of the loophole-free experiments done in 2015 was to say, it doesn't matter, we've missed some, we can still show, that it doesn't matter how our detection rates are so good that just because we've missed some doesn't affect the conclusion.
I see.
So that took a long while to iron out. People wanted to iron it out for many years before that.
Yeah.
That's an important loophole that has been closed in experiments, no longer available to appeal to the fact you've missed some photons.
That's fascinating. 2 questions from Howard Wiseman. The first is, you say the joint distribution for B and B prime exists, but I don't see why unless you assume HV or determinism or something equivalent to that.
No, you don't need, well, depends whether you mean physically exist or formally exist. Let me see if I can go back a few pages to where I'm saying that. First assumption, here we are. That these distributions exist, it just comes from no signaling. Actually, Howard, of course, being a great expert in this, will probably remember Fine's paper, where if you have 2 such distributions like this, you can just construct a distribution for all A, B, B prime, A prime, not just for 3 things, but for 4, assuming also joint invariance. So it exists. You can write it down. So, and I've written down one here, and this particular example, I've just got the probabilities that you can measure. And that's what I mean by exist. It's something that's between 0 and 1, sums to 1. The marginals are given by the distributions. It's quite analogous to Fine's derivation of a 4-quantity joint distribution, these 3 distributions. So in that sense, they exist. And many can exist. And if you can write down 2 that exist, you can show there's no signaling from Bob to Alice. If there's no signaling from Bob to Alice, you can show there are such joint distributions. This is a particular example. No determinism, no, what was the other thing that Howard mentioned? No
determinism.
No hidden variables.
Yeah.
When I say there's no hidden variables, you could say that, in a sense, this idea that the joint distribution, instead of hidden variables, you do need something that we know in quantum mechanics to violate the inequalities you can't measure directly. Complementarity. That comes down to these things exist formally. What do they mean physically? They have values. You can predict them. Even in the quantum case, you could predict these particular examples. But do they have any physical meaning? Bohr just says, no, they don't, because you can't measure them as the relative frequencies of an accurate joint measurement with B and B prime. So that's that question.
The second question from Howard was, the invariance principle you use is an asymmetric assumption from Alice to Bob. If you make it symmetric, then would it imply no signaling? It seems odd to use one symmetric principle and one asymmetric one to reveal inequalities.
Yeah. No, it's a good point. I just wanted to make things minimal, especially as writing a pedagogical paper in American Journal of Physics. Well, I played for a while whether just to do something more straightforward in PRA, Physical Review A, but I stuck with this. And that's why, so the first, they're both made asymmetrically. I could have just made this assumption both ways, as Howard points out, but I don't need to. Where it becomes important, the symmetry in a way is, the interesting symmetry is I can swap my labels for A and A prime, or I can swap my labels for B and B prime, or both at once. If I use those symmetries, I'll get another 3 CHSH inequalities. I can also permute the labels on my measurement outcomes, just instead of swapping the value, looking at what happens if I define yes as no and no is yes, for example, on my dice. And I'll get more CHSH inequalities that way.
Mm.
But if I actually swap the roles of Alice and Bob, I don't get any new CHSH inequalities of the type that I derive here. You'd need to look at non-CHSH inequalities. Yeah, so what I mean by that is it doesn't matter if I swap Alice and Bob over here, A to B and A prime to B prime, I'll get the same inequality. Okay, hopefully that answers.
Yeah, and just a final comment from Howard was he was just clarifying his second point by saying, for example, in standard quantum mechanics, the joint distribution does not exist, as you said. This would be Bohr's response.
Yeah, which is interesting though, because it does exist. You can write it down.
Yes,
but Bohr has to say more than it doesn't exist. He has to say, yes, it exists, but it's not a distribution in the sense of being directly measurable as a relative.
Yeah. Okay.
And so you have to bring in complementarity. But yeah.
And B. Dalton, is your invariance assumption equivalent to saying there is a deterministic hidden variable theory with a joint probability for all four variables?
Yeah, no, it's not. It's weaker. But if you, in the case where there's just two outcomes per measurement, which is the usual CHSH scenario, so here I haven't restricted the number of measurement outcomes. This inequality and this inequality still hold. In that case, so if you just derive this inequality, you don't need a deterministic hidden variable theory. But if you use all those symmetries I talk about, you can derive, in the case of two outcomes per measurement, a further 7 inequalities. If they all hold, for whatever your theory is, if all those inequalities hold, or from your experiments, then that's equivalent to saying that there is a deterministic hidden variable theory. So you can prove equivalences like that, but it's a more general result, I would say, because you don't have to assume determinism or hidden variables.
Joan Buccara makes a comment. I like that your derivation shows that what people have been claiming as an absence of local realism is now simply a consequence of complementarity.
Thank you, Joan. Yeah, if you're happy with complementarity, then yeah. And I started doing my PhD banging my head against the wall of Bell inequalities and thinking, oh, this shut up and calculate stuff, it's not good enough. But I've slowly come around to admiring Bohr's
point of view
on complementarity. So maybe not following the whole Copenhagen interpretation, but
yeah.
It's pretty amazing he came up with that so early as a central principle.
Yeah.
Yeah.
B. Dalton asks, does this 4 observable probability have to comply with locality in which P factorizes as P at X, X, P at A primed, X, P at B, times P at B primed?
Yeah, that's a subtle question for experts, I guess. But yeah.
You might have to calculate.
No, it doesn't directly. So maybe this relates, when he's talking about 4 distributions, he's relating to a point I was making in response to Howard's question. You can show from the existence of those joint distributions and the joint invariance assumption that there's in fact, a joint distribution for all 4 quantities. Does it have to factorize? No. However, from that 4 distribution, you can then construct a new deterministic hidden variable model in which you do get factorization. So in that sense, the answer is yes or no. You have to do some more work and you can get to such a model.
That's interesting.
Yeah, there's a lot of equivalences and implications that go on between the various usual statements of the CHS Bell inequality.
Yeah.
Of course, here I just want to reduce it to the statement at the bottom here.
Yes.
These things exist, they're not equal. So we have to chew on that.
Yeah, it's fascinating. Yeah. And final question from B. Dalton. Would a satisfactory hidden variables theory have to be non-contextual in the sense that the hidden variables are not dependent on the choice of measurement pairs?
Satisfactory, yes, depends what you mean. That's a very good question. it depends what you're happy with as satisfactory, but it has to be said that at the moment, I would say there's no satisfactory model where you allow this correlation, giving up, if you like, of complete free will.
Yeah.
That there's some common cause affecting things. But I'll just give one simple example which gives some hope we might find a nice satisfactory model. Suppose there's a quantity shared between two systems, and I can, and they're separated, and anything can happen with them. If they interact with other systems, we keep them in mind. All sorts of things go on while they're far apart.
Mm.
And I measure them. I can predict one quantity from knowing the quantity on one, I can predict the other on one. And you might say, but that's amazing. You've allowed all sorts of things to happen. You tell me you can predict I can infer what's going on. I say yes, because the quantity is energy and it's conserved, or the quantity is momentum and it's conserved. If you could derive this correlation between your choice of measurement and what a hidden variable tells you are going to be the results of the measurement as some sort of conservation law, that would be impressive and probably satisfactory. But that hasn't been done, and I'm not sure it can be done. So yeah, it's something I've played around with actually and found and not been successful in doing. So it's a bit sad.
And finally, from Paul, he wants to know, does weak measurement have anything useful to say about hidden variable and CHSH?
Yes. Yes, indeed it does. Let me get back to those three possibilities. So weak measurements, for those who aren't familiar with them, you can measure weak values of quantities, and the values that you get don't fall within the range of your observables. You can get negative weak kinetic energies by interacting weakly with a system. And you can get probabilities that are negative or perhaps greater than 1 for various results. So and more generally, not just weak probabilities, you get something called the Kirkwood-Dirac probability distributions, which can be negative. My thing's not working. But here we go.
Yep.
And that's another one where you can say, I've used the laws of probabilities to make my derivations, but they assume probabilities are positive and less than 1. What if we throw that away and allow negative probabilities? And my answer is yes, you can do that. But really, all that is another expression of complementarity, because those negative probabilities you can't measure as actual relative frequencies of a result that you measure, and 0 and 1 either happens or it doesn't happen. So again, I would say they're just an expression of complementarity, that those numbers aren't joint relative frequencies in any sense, because joint relative frequencies can't be negative.
All right. Well, thank you very much, Michael. That was a absolutely fascinating talk. I'll remind everybody, if they're interested, this will be on the AIP Theoretical Physics YouTube channel within a few days as we get it organized. So if you want to go over the details again, you'll be able to watch it there. Thank you, everyone, for coming. Thank you, Michael. We'll let everyone know when the next talk is coming up. I believe it's roughly in 4 weeks' time, towards the end of June. And we hope to see you all then. So have a good afternoon, and I'll bid you adieu. Thanks, Michael.
Cheers, Dave. Thank you.
Great.